In this part, we are going to discuss about Fourier's law of heat conduction and Fick's law of diffusivity. First, we will be covering Fourier's law of heat conduction. So, Fourier's law of heat conduction basically describes the rate at which heat energy is conducted through a material. It's named after Joseph Fourier, who developed this law in the early 1800s. To understand this, imagine a solid material, like a metal slab. If one side of a slab is heated while the other is kept cool, heat will naturally flow from the hot side to the cold side. This heat transfer happens due to the temperature difference, and that's where Fourier's law come into play. We represent this rate of heat flow per unit area using the equation Q by A directly proportional to T1 minus T naught upon capital Y. Q is a rate of heat transfer in watt. A is a cross-sectional area through which heat is conducted. T1 and T naught are the temperature at two different locations in the slab. Y is the distance between the two locations. This equation shows that heat flux is directly proportional to the temperature difference and inversely proportional to the distance. In this heat conduction, you will come across a term known as thermal conductivity, which is symbolized as small k. This is material property that quantifies how easily heat can flow through a material. For example, metals have high thermal conductivity, while insulators like rubber have low thermal conductivity. Do you understand that what I said? Metals have high thermal conductivity means greater value of small k, whereas rubber has low thermal conductivity means lower value of K. That is why rubber, wood, these are insulators because heat conduction is negligible or it's not easy in wood and rubber, whereas it is easy in a metal because of the higher thermal conductivity of the metals. Let us incorporate this thermal conductivity in the equation we studied earlier. Q by A equal K into T1 minus T naught upon Y. This is a basic form of Fourier's law for one-dimensional steady-state heat conduction. Now, let's look at a differential form, which is more general and useful in many applications. Small qy is equal to minus k dt by dy, where small qy is a heat flux in a y direction, dt by dy is a temperature gradient, k is again a thermal conductivity. The negative sign shows that heat flows from high to low temperatures. In this form, energy flux is represented by small qi. Transport property is thermal conductivity, small k. Temperature gradient is nothing but dt by dy. This tells us that heat flow rate per unit area is proportional to the rate of a temperature change with respect to distance. Let us visualize this. Initially, T is less than 0. The entire slab is a uniform temperature T naught. There's no heat flow because there's no temperature difference. At T greater than equal to 0, we suddenly heat the bottom surface of the slab to higher temperature T1. Now we have a temperature difference between the top and the bottom surfaces. As a result, heat begins to flow from the top to the bottom. No, heat is moving from bottom, which is hotter part, to the top, which is cooler part. This is the direction of energy flux. Energy transfer is shown by a black arrow in this diagram, which points upward, indicating the heat is moving in a y direction. The second diagram introduces us to a temperature changes over time. The graph shows temperature versus distance at different time intervals, starting from t is equal to 0 to t is equal to infinity. At t is equal to 0, only the bottom surface is heated, so temperature starts rising there, while the rest remains at t0. As time progresses, T1, T2, and so on, the temperature profile begins to smooth out. Eventually, at T is equal to infinity, the entire slab reaches the steady state conditions where temperature varies linearly from T1 at the bottom to T0 at the top. This graph beautifully shows how conduction works over time, distributing energy throughout the material until it reaches equilibrium. We are done with the Fourier's law of heat conduction. Here we are going to summarize it. Heat flows from high to low temperatures. Fourier's law quantifies that flow based on the temperature gradient and the material properties. It's foundational for understanding heat transfer in engineering and physics. I hope you people understood what I taught in this video or what I explained in this video. We are attaching numerical with this explanation so you can practice it, and then we will be discussing Fick's law of diffusivity.
This is the second question which we are going to solve in transport phenomena related to heat flux. This question is all about the Fourier's law of heat conduction. This question says that one side of a copper slab receives a net heat input at a rate of 5000 watt due to radiation. The other face is held at a temperature of 35 degrees Celsius, which, if steady state condition prevail, calculate the surface temperature of a side receiving radiant energy. The surface area of each face is 0.05 meter square and the slab thickness is 4 centimeter. Let's understand the diagram. This is the slab of thickness 4 centimeter, and from this side the slab is receiving a heat of 5000 watt by a radiation, and the area of the slab is 0.05 meter square, and the initial temperature which we have to find is T naught, and the final temperature is 35 degrees Celsius. So this is the formula of the Fourier's law of heat conduction, which is Q is equal to minus Ka dt by dy, where dt by dy is temperature gradient. Here, the first we have to calculate the heat flux, means Qy, means the heat transfer rate per unit area. So the heat transfer rate is given as 5000 watt and the area is given 0.05 meter square. So we got heat flux as 1 lakh watt per meter square. Now the calculated heat flux is 1 lakh watt per meter square, which we are going to put in this equation. So the Qi means after rearranging the equation, we get Qi is equal to minus dt by dy into k. And the integral form of this equation is Qy dy is equal to minus dt into k, After putting all the values given in the question and applying the limit of dy from 0 to 0.4 means the heat is going through inside by x is equal to 0 and the going outside at x is equal to 4 centimeter. We have converted centimeter into meter. Again, we have put the value of K means thermal conductivity of the copper is 398 watt per meter Kelvin. We have applied the limit means the initial temperature is T0 and the final is 35 degrees Celsius into dt. After integrating and putting the values, we get T0 is equal to 45.1 degrees Celsius. This was one of the simple problem of Fourier law of heat conduction.
Fick's first law of diffusion. This law describes how particles move from region of high concentration to region of low concentration. A process critical in a field like chemical engineering, biology, and environmental science. Let us basically begin with a basic setup. As shown here, imagine a species A diffusing through another species B in a y direction. At a bottom surface, the concentration of A, that is Ca, is at maximum. As we move up, the concentration drops to zero. This creates a concentration gradient which drives diffusion. The direction of mass flux is upward from high concentration to low concentration. On the right, you see a graph showing how concentration varies with the distance over time. As time increases from T0 to T infinity, the diffusion moves farther away. This is classical diffusion curve showing how concentration profile becomes more spread over with time. Fick's first law can be expressed in various forms depending on the quantity of the interest. You can express in molar form, which is denoted as Jy star, or in a mass form, which is small Jay. Talking about molar flux, it is written as J star Ay is equal to minus DAB into dCA upon dy. And mass flux, which is denoted as small Jay, is written as small Jay is equal to minus DAB d rho A upon dy. If you have mass fraction, you can write small Jay is equal to minus DAB into dWA upon dy. Each form is used depending on whether you are working with a mole fraction, mass fraction, or concentrations. You can choose the appropriate term as per your requirements. The most common form of Fick's first law is J star Ay, which is molar form, where J star Ay is a molar flux of A in a y direction. How much A is moving per unit area per unit time is molar flux. DAB is diffusivity, a transport property that tells how easily A diffuses in B. dCA upon dy is nothing but concentration gradient, the driving force for diffusion. The negative sign here indicates that diffusion occurs down the concentration gradient. Now, let us talk about how diffusivity DAB depends on pressure and temperature. Diffusivity increases with temperature and decreases with pressure, and it follows the relation DAB is directly proportional to T to the power 3 by 2 divided by capital P. So, if temperature increases or pressure decreases, particle diffuses faster. This is intuitive. At higher temperatures, molecules move more rapidly. Diffusivity also varies significantly depending on phases of material. Gas, it is around 10 to the power minus 5 meters square per second under atmospheric conditions. For liquid, it is around 10 to the power minus 9 meters square per second. For solid, much lower, between 10 to the power minus 10 to 10 to the power minus 14 meters square per second. This shows that diffusion is faster in gases and slowest in solid due to the greater freedom of movement in gases. Lastly, we can derive an integral form for steady state diffusion where the molar flux becomes small ma upon capital A equal dAB into Ca naught upon capital Y. This gives the total mass of A transferred per unit area based on the diffusivity, initial concentrations, and thickness capital Y. This form is useful for estimating how much of a species will diffuse over a given time and area. What we studied is Fick's first law helps us quantify diffusion driven by concentration gradients, whether you are dealing with gases, liquids, or solid. This law is a powerful tool to analyze mass transfer. We are attaching a small numerical for your convenience so that you can implement it to a real life or in a numerical form. So please attend it.
This is the one of the simplest problem that I'm going to solve in front of you. So this question is about Fick's first law of diffusion. So the question says that air is at atmospheric pressure and 95 degrees Celsius, flows at 20 meter per second over a flat plate of naphthalene 80 centimeter long in the direction of flow and 60 centimeter wide. Experimental measurements reports the molar concentration of naphthalene in the air Ca as a function of distance x from the plate as given below. Determine the molar flux of naphthalene from the plate surface under steady conditions. Diffusivity of naphthalene at 300 Kelvin is given as 0.62 into 10 to the power minus 5 meter square per second. So this is the data that is given to us to solve the question. This is the data between the distance and the concentration. So I have plotted a graph and let me show you the behavior of the graph. So here I have written the data that is given in the question, and now I'm going to plot the graph between the distance and the concentration. So this is the graph between the distance which is in x-axis and the concentration which is in y-axis. Now I will show you the equation of the line that we have got from this. So this we have got the equation of the line which is y is equal to minus 0.0145x plus 0.1247. So the slope of the line is minus 0.0145x. But here the equation is dV is equal to 368 into dV at 300 into temperature into the power 3 by 2, which we get 0.84 into 10 to the power minus 5 meter square per second. And the molar flux is asked at x is equal to 0, means the concentration gradient which we have to find should be at x is equal to 0. So here I have calculated dCA by dx as x is equal to 0, which is 0.093 minus 0.117 by 10. I have got minus 0.002016. So this is the slope that we're going to use in this. And the value at DAB at 368 Kelvin is 0.84 into 10 to the power minus 5 meters square per second. Now the overall molar flux we have got is 2.02 into 10 to the power minus 6 mole per meter square second. The star above the JA indicates the molecular flux. My aim was to plot a graph and show you the behavior of the graph. So we get that concentration is decreasing with increase in distance. So you can easily see from the screen that the concentration is continuously decreasing with increase in distance, which has been shown by this negative slope. And this negative slope indicates the continuous decreasing. So I have concluded three things. First, the diffusivity is a temperature dependent and increases with temperature, calculated using the T to the power 3 by 2 relation means this. And Fick's second law relates flux to the concentration gradient, showing how naphthalene evaporates into air. And the third that I have concluded is molar flux at the plate surface is 2.02 into 10 to the power minus 6 mole per meter square second, which has been asked in the question. So this was the problem that we have solved.